Hello everyone, I'm Dušan Isailović, an assistant professor at University of Belgrade, Faculty of Civil Engineering. And today I'll talk about 3D city model conversion to BIM for automatic material quantities assessment. So the first question would be, why would anyone do that? And the answer is to be able to map the embedded material quantities at a large city scale, or more specifically, to improve the circularity of construction industry in terms of providing information on embedded materials in the existing building stock to the investors who are willing to keep the materials in the loop. Saying that, this work is a part of Horizon Europe project CircBoost, titled Boosting the Uptake of Circular Integrated Solutions in Construction Value Chains. So how could one assess the quantities of materials currently? There is a top-down approach, which is basically calculating differences between material inflows and outflows. It is relatively fast, but it lacks a detailed spatial distribution, which makes it difficult to plan and forecast reuse and recycle. There is also a bottom-up approach, which is based on material intensity coefficients, or mix, which are basically material quantity in mass or volume, derived by some general building geometry, which is also volume or building footprint area or something similar. It is way more accurate, but it is extremely time-consuming to calculate each one material intensity coefficients for each material. So this is how we can calculate the exact quantities, but which materials do we have in a building? That information can be retrieved from so-called building typologies, which are division of buildings from the building stock into categories, or so-called archetypes. For each archetype, materials used for each common data element type are specified. And also, for geolocation and geometry of buildings, we can use GIS systems, and we can easily derive height and building footprint area to multiply with this mix. So this is the current state of the art. And our idea is to improve that state of the art by taking all this information that we have. And as inputs, we have really a 3D city model in a CityGML format at level of detail 3, which is quite high. We have also national building we use national building typology, in this particular case, the Serbian one. And we also use the cadastre data for construction year and height, because national building typology depends, the type in it depends on building construction year and shape and some more parameters. So the idea of our new method is to look at separately at building exterior and interior, and the reason is because we have geometric representation of its exterior in a 3D city model, whereas for the interior we don't have that. And to have one approach for the exterior: walls, ground floor, roof, doors, windows, and to model it, to make BIM of it. And for the walls, doors, and floors, we would use the old school method, so this material intensity coefficients. So for the exterior, we take the surface, which is a representation of each elements in CityGML file format, and to basically extrude it for the amount of layer thickness. So adding layers, assigning material information to it, which basically means having a building information model on the scale of the entire building. And if we perform the material takeoff, that would get an exterior material quantities. So for the interior, we use footprint area of the building and multiply it by various material intensity coefficients, and that's how we get interior material quantities. So the first step would be to identify archetype by looking into buildings' construction year and shape. And then to model a wall, we would take the description for the building typology, get from there layer materials and layer thicknesses. From GIS, we would get the wall surface converted to BIM, and then to extrude, to multiply, offset, and extrude this surface for the number of layers that we have, and of course to assign materials to it. Okay. This gets us a problem with wall overlaps and at corners, which we eliminate that currently only computationally, but we plan to do it also graphically. And for ground floor modeling, the story is pretty much the same. It is pretty much straightforward to extrude this surface. For the roof modeling, the situation is not the same. We need to make one approximation. In order to keep the approach consistent, we are representing the roof structure, usually the wooden roof structure, also as a one solid layer by calculating the volume of the wood and basically distributing it to the roof surface. So that makes us a solid wood layer. So yeah, basically the rest is the same, taking GIS surface and turn it into BIM and then extruding it. For the windows is also similar as with the roofs, so representing window frame as a solid layer. Yes, and the rest is the same. So we managed to automate this by, first of all, converting CityGML to IFC by kit model viewer. That gets us quite rough IFC structure, which we adjust later. We use archetype identifier, so manually assigned archetypes to each building, and also we have just a Python dictionary specifying every material layer with its material type and thickness. So we iterate to each building in a model, assign type to a building from the archetype identifier, generate lists of material layers. Then we again iterate through buildings in a model for each element in a class, and iterate to each element instance in a class to replicate an offset element surface for the amount of material layer thickness. And then we comply material layers to IFC semantics. So I will just show a very, very general structure. So I intentionally use this IFC surface because this is the representation in this simple conversion by kit model viewer. And as opposed to one representation of one element, now we get, in this example, 3 elements. So we get 3 different elements. So we don't use this IFC layered structure approach, but we just completely separately model each element as a separate layer. And then, yeah, we need to multiply these IFC element instances too, and to, of course, to assign or to associate with the geometry representation. And at the end, we just associate materials to each separate IFC element. For data models, we use CityJSON, so JavaScript notation of CityGML, IFC. The code is written in Python using CGIO library and IFC OpenShell, and we used extensively a Blender environment. We tested our approach to, a case study, in a case study of at the Belgrade quarter, including 37 residential buildings. So for validation, we had the exact takeoffs from the documentation-based BIMs of buildings, and also we used mix for some other buildings. And results proven that our approach gives us 70% accuracy for all materials categories except for wood, for older single-family houses, so built before 1960, and accuracy drops to 40% for multifamily housing constructed after 2011. So the reasons for these are, of course, the first one for woods is making this approximation of solid layer of wood structure. So we are improving our approximation, so including also wooden columns and also some sloped columns and beams. And for this newer buildings, the problem is variable architecture on different floors. So we cannot use the same building footprint area to multiply with material intensity coefficient. So we're also working on this. So except from that, the improvements we will work on further is medium floor modeling, or also interior floor walls and doors modeling. So predicting what can be inside. Also, walls overlap geometry correction, as I mentioned. For that, we use topologic pi for prediction of the internal elements. Also, some visual programming in Blender. And that would be all from my side. Thank you very much.